So on exam 4, there was a lot of different hypothesis tests that you had to deal with. And that presents a little bit of a challenge. Now, most of the hypothesis tests came from chapters 8 and 9. And in those chapters, you had things like mu, which was for hypothesis for a population mean. Or there was sigma. What does sigma measure? Standard deviation. Good. You always also see variance or variability. So there's a lot of ways you can refer to this parameter. You don't necessarily have to refer to it directly by saying standard deviation. And likewise with P. What does P stand for us in this one? Yeah, it's proportion. But there's other things you might see instead of proportion. It might not be directly written as proportion. You could also see rate. Anything else? Yeah, percentage. So when you're seeing these keywords, it's telling you what parameter that should be part of your null and alternative hypothesis. Another thing you're going to have to decide is one population versus two populations. Okay. So let's look at the exam that you just took. And at the top here are all these different hypothesis tests. So there's 10 of them. There's a lot to choose from. Now, it's kind of up to you. You can start by deciding how many samples you're dealing with, how many populations you're dealing with, or you can just start by figuring out, well, what parameter I'm dealing with. It doesn't matter either way. Let's go with the parameter first. So in problem number 1, it says trials in an experiment with a polygraph include 99 results that include 24 cases of wrong results and 75 cases of correct results. Use a 5% significance level to test a claim that such polygraph results are correct less than 80% of the time. So right there, 80% of the time, or correct less than 80% of the time, that's telling you the parameter that you're testing in this case. So what is it? What parameter am I testing here if I'm going to be right less than 80% of the time? Yeah, it has to be proportion, right? You're not talking about a mean. You're certainly not talking about a standard deviation. So it's a proportion. Now I got to decide, is it one population or two populations? And, you know, I can understand a little bit of confusion here. But if you look back at the problem, it says you had an experiment, and these are the results. You had 99 people in this experiment, or 99 tests anyways, and it was 24 wrong ones and 75 right ones. But that's still just one sample, one population. So what letter does that correspond to then? Yeah, A. Proportion, one sample. Done. Let me write down the null and alternative hypothesis. Your alternative hypothesis is kind of hinted at right here. Polygraph results are correct less than 80% of the time. So for problem number 1, that would be P is less than 0.80. Now that has to go in which hypothesis? The null or alternative? Has to be in the alternative. So that's HA, HO would be P is greater than or equal to 0.80. Of course, on my stat lab and in the book, that's just going to be P equals 0.80. That's okay. I accepted either one. Okay, let's try the next one. Listed below are the student evaluations of male and female professors. Use a 5% significance level to test the claim that female professors and male professors have scores with the same variation. All right. I'm hoping that it's kind of in your face on this one in terms of what parameter are you testing. Are you testing a mean, a standard deviation, or a proportion? Which one are you testing here? All right. I'm hoping that more than just Lena knows what parameter we're testing here. Oh, is it Heather? Okay. I'm sorry. I wasn't looking. I was just using the direction it came from. All right. So the two people. But I'm hoping that you're all seeing that this one has to be standard deviation. Okay, you're talking about the variability there. The next thing we need to decide, is it one population or two populations? Well, let's look back here. We've got male and female professors. Each one has a row of data. What do you think? Want to go out on a limb? How many populations are here? Two. Yeah, two populations. So if it's two populations and it's variability, then, oh, there you go. Two population variances / standard deviations. Done. Well, I guess we should probably write down the null and alternative hypothesis. So let's do that. I believe that when I wrote out the answer key, I did this. I said sigma sub m equals sigma sub f. And the alternative was sigma sub m is not equal to sigma sub f. All right. You don't have to use m and f. I like that. I feel it's more descriptive, but you don't have to.
Professor,
Yes.
do you mind explaining why are you writing like M and F? Oh, male and female?
Yep.
Oh, sorry.
Male and female. Yep. All right. Thank you. Let's see here. M&M plain candies are distributed with a proportion listed in the table below. Samples of a huge bag of M&Ms gets the observed column of data. Well, that word observed is kind of directing you in one fashion or another. Now, you've got all these different rates and probabilities, whichever way you want to think of them, but it's not A and it's not, where's the second one? It's not D. It's not proportion 2 samples or proportion 1 sample, because you've got a lot of different numbers here. Now, are you talking about means and standard deviations at all in this one? Are you trying to match observed and expected? No. Nothing about means or standard deviations here. So that actually eliminates a lot of stuff. It eliminates the entire first column. It eliminates, a couple of the answers on the second column. So you're left with correlation, chi-square goodness of fit test, and chi-square test for independence. Chi-square test for independence is going to be a cross table or contingency table. And that's not what we've got here. It's not a correlation. They're not asking you how to correlate things. So it kind of works down to a chi-square goodness of fit test. Goodness of fit is how well does your observed values match the expected values. So let's directly hint at that right here. Your observed column of data. You want to see how well it matches your expected column data. How well does the expected values fit the observed values? Does it fit well? Does it fit good? Goodness of fit test. So the answer there would be I. And there's a couple ways you could write out this. The way I wrote it out, as I just said, P sub R was 0.31 or 0.131. P sub O was 0.205, and so on. I wrote out all of them. And the alternative hypothesis is that at least one is different. So there you go. Let me see if I can't pull up something on one of my favorite pieces of new technology, Desmos. So y equals, I don't want capital Y equals mx plus b. All right. Remember what mx plus b is all about? That's m is what? when we talk about the equation of a line? M is the slope. So if your slope is, positive, it's as you move from left to right, the line's getting taller. If your slope is negative, the opposite happens. As you move from left to right, things are going down. But there's one point here in the middle that's of particular interest, and that's when your slope is 0. So it means no matter what value of x you have, your value of y is always the same. It doesn't matter what x is. That's not true if x is, say, 1. If x is 1, then if m is 1, then when x is 5, m is 6. When x is 6, y is 7, etc. So there's a nice relationship. You put in a value of x, you get out a value of y. But the big thing is that it's something different than 0. Because if you had 0, that means there's no relationship, no linear relationship at all between x and y. You're just going to get the same answer. Let's go back to the exam here. Listed below the duration times in seconds and time intervals to the next eruption for randomly selected eruptions from Old Faithful Geyser and Yellowstone National Park. Is there sufficient evidence to conclude that there's a linear relationship between the duration of times and the intervals? Between duration times and the interval times. So how long it erupts for and the time between eruptions is what you're looking at. Well, looking for a linear relationship. That kind of rules out a lot of stuff, doesn't it? It rules out proportion one sample, mean one sample, standard deviation. It rules out this first column. It also rules out some of the stuff on the second column. We're not looking for a mean. We don't have anything about two population standard deviations. Correlation. That one's kind of interesting. In fact, I took the time to put down, recall this is the same as a test for significant regression. So if there's a correlation, then what do I use? What signifies a correlation? What's the variable, or excuse me, the parameter, I should say? Does anyone know? Rho. Good. Now, if there's no correlation, really what that means is that there's no linear relationship. There's a couple ways you could test this, but if there's no linear relationship, that means your slope is 0. That's equivalent to rho being 0. So the correct answer here was rho equals 0, and rho is not equal to 0. You could also say that if this was, say, a linear regression, beta equals 0 versus that beta 1, I should say, is not equal to 0. That's assuming that you're dealing with this model. That is, y equals beta 1 x plus beta 0. You got a slope of 0. Meaning, you might as well just write y equals some number. That x and y doesn't share a meaningful relationship because no matter what the value of x is, the value of y is going to be b sub 0. Okay, these two are equivalent. This is the answer that I expected. I would have given credit for that as well. Let me check the chat here real quick. All right, thank you, Michael. Let's get rid of you. There we go. So the correct answer on this one would have been H, as a correlation. All right, that moves us down to this one. The amount of arsenic in samples of brown rice are given below for samples from 2 states. The amounts of arsenic appear to be, do the amounts of arsenic appear to be different in the different states? Test a claim at a 5% significance level. All right, so it has a feel of being back in chapters 8 and 9 again. testing parameters. So let's see if we can't figure out parameters and what we might be testing. So going back to the top here, same amounts of arsenic in brown rice. Well, is that saying anything about proportion or rates or percentages? Can I eliminate that one? How about variability? Was there anything about variability there? Standard deviation, variance? No. Does it make sense that the average or the mean would be the parameter that we're testing? Yeah, because you're looking for, on average, how much arsenic is in these grains of brown rice. So yeah, it makes sense. So we've got mu there. Are we dealing with one population or two populations here? Two populations, good. So let's look back at this here. You got two populations and we're testing mu. There's actually two letters that could satisfy this, and I think I gave partial credit for one. But which two letters would satisfy this, or could satisfy this? We need to think a little bit further. E, good. Mean, two samples, independent. And what else? F. So basically we have to decide, are these dependent or independent? Now, if you grab some rice from a bunch of different farmers in Ohio and did likewise with farmers in Michigan, do you think the amount of arsenic in each sample is going to be related to each other? Farmers from Michigan, farmers from Ohio? No. So that argues that these samples are independent. So that would be this one. Now, as far as the null hypothesis is concerned, so the correct answer there would be E, and then stating the null alternative hypothesis. Let's see, want to test a claim that there's different, that they're different. Now, if they're different, then let's see, get back here. 5, H sub 0, H sub A. If they're different, then that would be this kind of a hypothesis. Mu sub M and mu sub O. And then the null hypothesis would be that mu sub M equals mu sub O. So, there. Question?
Okay, so on the old exam, you had that question as the ANOVA answer.
Yeah, I did.
It was 3 states, and on the test, it does say 3 states. It doesn't say 2.
Yeah, it had the 2 data sets. Yeah, so.
So that we were just talking about how that confused us.
Sorry about that. Yeah, there's data from 2 states. So yeah, if I had 3 states, then it hopefully would be pretty clear that, you know, there's 3 states, you have 3 samples. That's a one-way analysis of variance. So yeah, I just deleted that because at that point when we were taking the test, I hadn't covered analysis of variance. So that was an easy way for me to kind of get another problem without really having to work so hard. So sorry about that. Let's think here. And of course, a couple Saturdays ago, we actually proved that mu sub M is greater than mu sub O, but that's a different story. And you guys got a lot of extra credit for that. So, all right. In this case, we don't want mu sub M to be greater than mu sub O. We don't want more arsenic in our rice than them. Okay, and the last one like this. The table below lists the frequency of wins for different post positions through the 141st running of the Kentucky Derby. A post position of 1 is closest to the inside rail, so the horse in this position has the shortest distance to run. Okay, so you got 10 post positions represented here. Do they all win with the same frequency or not? That's what we need to test. So, well, what can we eliminate? let's take a look at what we can eliminate. Is there something we can eliminate here of all these? Somebody in the chat, throw out some letters or something that we can eliminate. Or somebody here. What can I eliminate? Yeah, it certainly is nothing about standard deviation here. All right, so we can eliminate that. All right. So now we've got, instead of a 1 out of 10 chance, we got a 1 out of 8 chance. Let's keep going. What else can we eliminate? Yeah, we're not talking about means. We're not talking about the average finished place. All right, so that throws out 3 more, B, E, and F. All right, so now we're down to a 1 in 5 chance if you're just pure guessing. Well, it's getting better. Is there anything else I can eliminate? Which one? Yeah, it's not really a correlation. I'm not correlating how they finished with where they started. So I can eliminate correlation. So that's good. So we're narrowing it down. Let me see. It's not a proportion 1 sample. We're not saying that 50% of the horses that win are going to finish from the first slot. It's not a proportion 2 samples. We've got like a lot of different positions here, right? We've got 10 positions. So it seems like we've eliminated pretty much everything except I and J. Which one of these do you think works? Is this another goodness of fit test, or is this a test for independence? Am I trying to see if one is independent of another, or if I'm trying to see, does my data, my observed values, match my expected values? Which one do I have here? I got to vote for I. Anyone else? Got a couple nods here. Yeah, it's I. So if the claim was correct, then the likelihood of winning is the same for all positions. That is, I should see, however many, I should see about 14 wins per position. Well, I do and I don't. I mean, boy, it kind of sucks to be in position 9. You're not winning from there very often. I don't think I'd be putting my money on them. 6 and 7 don't seem to be doing so good either. But pole position, number 1, yeah, that's not doing bad. He's doing pretty good. So this is a goodness of fit test. How well does your observed data match your expected values? So in this case, I'm guessing not so well. Now the way you state your null hypothesis is that P sub 1 equals P sub 2 equals P sub 3 all the way down to equals P sub 10. So they're all equal. Now on the answer key, I also put equals 1/10. I didn't have to. I mean, logically it's kind of implied, but I didn't have to. I also accepted people who just simply wrote that each position has an equal chance of winning. So this was kind of the exception to the rule on this test, that I accepted words rather than something written with probabilities and parameters. Okay. Let's take a look at problem number 7. And in problem number 7, we'll start with the extra credit part of this. There's 5 answers that you need to put, and you've got 8 possibilities here. So this is a little bit of review for your final exam. I said, how many different ways are there that you can answer these 5 questions with 8 possibilities? Well, it comes down to something old and familiar. Does order matter or does order not matter? So combinations versus permutations. Which one's which? Which one does order matter? With combinations or permutations? All right, I've got one person answering. Oh boy, you better have this one straight a week from Monday. I don't see a lot of confidence out there. I'm pretty confident. I'm 95% confident that I don't see a lot of confidence in your faces when I look out there. Order matters with, all right, you want to cast a deciding vote? I've got 2 people that say permutations and 2 people that say combinations. So what's the deciding vote? Permutations. Winner, winner, chicken dinner. Yay. So yeah, order matters with permutations. All right. Now, do you think order matters in this case, or should I use combinations or permutations to calculate this one? Do you think the order matters? If you give me the right 5 numbers in any order, that I'll give you credit? Probably not. You could try it. But no, order does matter here. So it would be 8p5. And it's like 6,720 or something like that, I think. But the order does matter there. Now, let's work through these and kind of hit them one by one. Now, what does it mean if you have a value of r equal to 1? A linear correlation coefficient of 1 or -1. What does that mean? It's a perfect straight line. That is, your data are flawless. So let me get back here. So r of -1 would be something like this. A perfect straight line. That's an r equal to -1. R equal to +1 is the same thing in the positive direction, but it's a perfect linear correlation. So let's start out here and we'll kind of work our way backwards up this thing. Is that a value of r equal to -1 here? Is that a perfect linear correlation? No. All right. Well, what's the next best thing if it's not -1? -0.99. Yeah. All right, that makes sense. Okay. So we can eliminate actually 2 of them, right? It's not -0.99 and it's not -1. So, okay. How about this one? Is that a 1? No, you can eliminate the 1. Is it a 0.99? Is it really tight, but it's just not quite perfect? So you can eliminate those first 2. It's not either of those. How about 0.7? Does that seem realistic here? Yeah, that seems reasonable. If amongst your choices, it's either 0.7 or 0.3. It has to be something positive, 0.7 or 0.3, but I think I'm liking 0.7 a lot better here. The next one, is this positive or negatively correlated? Negative. So there's really only one choice left, right? We already used -0.99, and it's certainly not that anyways. So it's -0.3. It's really kind of your only choice there. How about over here? Well, we've used 0.7. It's not 1 or 0.99. So the only one left is 0.3. And that means the last one would be the 0. Just no correlation there.
So that confused me when this story started.
You're gonna say the same
I
thing.
thought it was like a rainbow thing,
Yeah.
and that made no sense to me.
Which one? This one?
Yeah. So when we were doing like AS stuff, a 0 always showed like a rainbow.
Well,
So confused on that because there.
well, 0 correlation means there's no linear relationship. So knowing the value of x doesn't tell you anything about the value of y. I did give a different example. I'm sorry that I see what you're saying. By the way, I graded that one really generously. I see what you're saying, that in your mind, and I appreciate the feedback, but basically what you're telling me is that you thought the only time you had r equals 0 is that it looked like that. R equals 0 really refers to the fact that you've got randomness. It's just a big mess. There's no linear relationship at all. If you fit a line here, it might have a slight slope like that, but for all intents and purposes, the line that you should use to relate these things is just flat, because knowing something about the value of x tells you nothing about the value of y. And that's what you see here, is that, yeah, I could tell you x is 10, but it tells me nothing about y. I mean, you could have equally up here or here. You know, it just doesn't give you any information. There's no real linear relationship amongst those. Whereas some of the other ones, if I tell you x is 10, yeah, it gives you a hint about where y could be, you know. So, no, it's good to know. I really appreciate the feedback here, because I can see the confusion there, and it explains a little bit of some of the answers I got here on this test for that. So, thank you. Just know that the extra credit that I gave you was worth like 5%, which was worth more than the one that you missed or might have missed on this one. So, my bad. Let's see. Let me go back here to find the rest of this. 5 things discussed in class. Those, I think I told you directly when we talked about the cause and effect relationship lecture that I wanted those 5 things. They were there. You can look those up again on the answer key. This one you guys did pretty good. This one has a habit of showing up on the final exam. You should know this. So this is a way to judge how good your regression is. And you don't always have to have a linear regression either. The value of r squared can help you out in a lot of situations. It judges how good your model is. How much of the variability in y is explained by knowing the value of x. It's exactly what I was looking for. A lot of people gave me exactly that. But the thing is, r squared is more general than that. You know, you can use it not just for a linear regression, but for all kinds of different shapes of regression. Maybe that's something I should show you a little bit of. But you know what? Let me see if I don't know if I got it. Boy. You know, I'm not even signing in the right thing here. Yeah, I'm sorry. But I did get paid to do consulting work for a friend of mine, and I fit different models as to how concrete would dry. And to help decide which model we liked, we looked at which one had the largest value of r squared. Now, r squared goes between 0 and 1. You're only going to get an r squared of 1 if you have an r of 1 or negative 1. Meaning you had a perfect linear relationship. So knowing the value of x exactly tells you the value of y. But I got some pretty good r squared values. And to choose amongst them, we chose the one with the highest r squared. Because they were all pretty close. We just said, I like this one best. Okay. Let me go back here. What sign would you give the value of r here in this data set? It has to be negative, right? Now, what I gave you in this one was the value of r squared. So r squared in that one was 0.9025. If you want r, you can take the square root on both sides. But keep in mind from your work in algebra before you came to this class that there's really 2 roots here, a positive and negative one. So although you can get 0.95 from your calculator here, what you need to know is that that has a negative slope. So the correct choice there would have been a negative 0.95. And a lot of you got that, and that was good. I remember apologizing about the unsavoriness of that one example we did with, what was it, that nurse. But I said, we're going to stick with it because I want to tell you that when you do this kind of an analysis, it shows association, not causation. And the whole point of that problem that we did was Kristen somebody, can't remember her name. What is it?
Gilbert?
Yeah, Kristen Gilbert, was that, one does not necessarily cause the other. That all you can show in an analysis like this is association, not causation. So that was the big point of this one. This one, people didn't do so good on this one. And I actually tried to give a real big hint on this one as to what kind of analysis that we could do. Does anyone see the big hint that could help you out with setting up HO and HA? I mean, if you looked at it, and I didn't necessarily need to give you the data here, but I did, gave you the data. But what's in the data table that is kind of a clue? Yeah, mu1 and mu2. It's right there. So I was like, okay, here it is. You're going to be testing for the equality of means in the independent case. Case closed. Oh well, if you missed it, hey, there are worse things in life. This one, let's see, number of words test. So the null hypothesis in this one comes based off of this claim. Number of words per page is greater than 47.3 words. All right, so what parameter is that? Is that going to be a mu, sigma, or p? It's going to be mu. So our claim is that mu is greater than 47.3, and somehow I switched out of the wrong thing here. So mu is less than or equal to 47.3. That's the null hypothesis. This is the alternative hypothesis. A lot of people struggled with the part that follows next, and that is describe what a 95% confidence interval for this data is. And it is that we can be 95% confident that the true value of mean is between 44.2 and 58.99 words per page. That's it. That's all I was looking for, is just to describe what it means in words for this to be your confidence interval. Okay, some people thought deeper into that than I really meant. But the next one asks you, does this confidence interval match our conclusion? Now, your conclusion when you did the above hypothesis test was to fail to reject H naught. So you didn't reject it. This is what we believe is true. Does this match your confidence interval? Now, some of you got a little bit tongue-tied with the number 0. That's when you have two populations. We only have one population. Okay? And if you look at that 47.3, it fits right in here. That's where we believe that our population mean is. And guess what? We didn't reject it. So, this sometimes would be written as mu equals 47.3. And if we think it could be this, because it's in my interval, then I shouldn't be rejecting my null hypothesis. Those two match each other perfectly. So we fail to reject, and that value is in our confidence interval, where we think it should be. So we're good. Okay, any comments or questions? All right, homies, anyone there? All right.